collection of multiple programs, code snippets, chronologically ordered. Here you can see the biosim as it is within the Kbase narrative. This is great to have on here because it allows any biologist with access to Kbase to use biosim and access its tools and its instances. Something that biosim uses or can use is known as combinatorial interaction testing, which I will refer to as CIT. CIT is used in software engineering and computer science, designed for systems that have a large amount of configurations or settings to test. The way it overcomes those large configuration spaces is by creating a systematic sample of the input or the configuration to then run test them. This allows us to get meaningful results from much larger input spaces that would normally not be featured. Currently, there are some limitations of the biosim as it is on the Kbase narrative. Here you can see a section I took from the example for the guide for biosim on the Kbase narrative. The guide mentions that while you can exhaustively run some of Kbase's inputs on biosim, it can take a while. So in this case, they've provided a CIT sample known as a covering array that you can see in the table in the center of the screen. This covering array provides 6 samples or 6 tests that effectively represent the exhaustive 128 tests that would normally be taken through biosim without CIT. However, the key thing to note here is that this covering array was not generated in Kbase. Rather, it was specifically generated for this one case. So the question is, if a biologist would like to use biosim or apply software testing techniques to biology on Kbase, how can they take samples like CIT and apply it to their program if it's not available on the website? The objective of my research was to adapt software testing CIT methods for use on Kbase by biologists and bioinformaticians in order to apply efficient testing to media interaction, with media being biological objects and data. And secondly, publish the adapted tool for public use primarily on the Kbase narrative system. Our solution came in multiple parts. The first thing to keep in mind is that the CIT software testing tool which we selected is older and it's designed for software testing, not biological testing. So the question is, how do we take something that is designed for software configuration files and effectively apply it to biological media? Well, the first step was employing something called Docker containers. You can think of Docker containers as a lot like lightweight virtual machines. They provide much of the same encapsulation and compatibility. In this case, this encapsulation is crucial because many of the dependencies of this software testing tool may be outdated or no longer functional. Secondarily, it allows us to interface with the Kbase narrative environment without worrying about any cross-compatibility or language differences. You can see here I chose a short snippet from our encapsulation to show that the Docker container is also portable and is downloaded from a remote server, allowing it to be run on different computers. The second step of our solution was interfacing with the Kbase software development kit. The Kbase SDK is very different from the expected environment of the CIT tool in its original conception. The SDK speaks in terms of media or biological objects, compounds, and other systems biology data sets. So the question is, how can we take those media and biology-oriented data sets and translate them into software configuration files for use by the CIT tool without losing any important information, while still being able to reconstruct that same media at a later time. The approach we went for was not to modify the CIT tool, but rather build a translation system to completely change media files into software configuration files before passing to the CIT tool. I chose this short snippet from our program because I believe it effectively demonstrates our methodology. You can see on line 177, we're creating an entirely new input file. That is the assembled software configuration file from our media. The third part of our solution was the user interface section. How can we display the transition from media to software config files effectively and make it intuitive for the user so that they may edit it and make additions or subtractions or selections as they would like to? Well, the answer might not be as complicated as it would seem. You can see here we have a quick snapshot from the user interface in our uploaded CIT tool. We start with media, the organic compound carbon D-glucose. Below it, we've selected two settings, two compounds, and represented them as settings. We have compound 003 and compound 0007. The way we represent these in a configuration file is as explicit settings with the values we want to test with potential values of settings. Here we have respectively 0 and 20, 5 and 7. The result of this modeling method means that we can take any media and represent it as traditional software configuration files. Here I have a more explicit translation between the two. We have a subsection of the media file, compound 27 and compound 30, with the two relevant values we want to test in the far right column, -100 and 5, -100 and 100. You can see how we translate that below, with compound 27 having -100 effectively represented by 0 and 5 represented by 5, with the same in the next setting below. If we zoom out a bit, we can see the full compound makeup of carbon D-glucose. Here we're seeing 10 entries out of 20 total. These 20 entries each have two potential values at minimum that we may want to test the interactions of. What this means for a tool like Biosim is that if it were to exhaustively test all the interactions, we would have at a minimum 2 to the 20th power of potential interactions to test. That's nearly unfeasible, considering that carbon D-glucose with its 20 entries is not an exceptionally large media file. However, if we combine the CIT tool designed or adapted for biological work with Biosim, it gets a lot more practical. Here we can see the output of the tool when it was run on the table that we just saw in the last slide. What we're seeing here is 3 sections. We have the list of compounds in the order they appear. We have the sample size, which tells us the number of tests. And we have the array of tests itself. You can see here, we have in order the labels of the columns, which are compounds 149, 99, 67, etc. In the very first row of our 2D matrix of tests, we can see that compound 149 is represented by 0, compound 99 is represented by 100, and so on. Each of these rows is a test combination, which combinatorial interaction testing found as a sample to systematically test our input state. That means that out of the 2 to the 20th power potential interactions, CIT has reduced this to 8 to use with Biosim. For the next steps of our research, we are working to apply formal acceptance to public use on Kbase, which will be available after review by moderators. Before I end this presentation, I'd like to give special thanks to Michaela Cashman, who implemented the BioSynth program on the Kbase narrative system, and to Dr. Myra Cohen, my mentor, who provided immeasurable help and answered many questions. Thank you.
We have plenty of time. We have plenty of time. Are there any questions? Yeah, well, I'm not an expert in this area, but I got interested in a couple of things you mentioned. So let's start and you mentioned Jupyter Notebook. Did you mention Jupyter Notebook at the beginning?
I did.
Yeah. So that's what I'm curious. So this, so you're saying this system for bioinformatics exploration has a format like a Jupyter Notebook. Does that mean, let me just does that mean you can interleave a little bit of text, a little bit of code, run it in the browser, this kind of?
Correct. It is not one-to-one identical, but that is the closest analog that is like. You can interweave programs, code, snippets, text, chronologically.
Okay, that's nice. Okay, that's one question. Another question, I guess I lost a little bit apart from, you have a combinatorial problem, obviously, search over a huge space, potential options, and it's been reduced. So where is it? Is that a part of the package that is reducing? Who is reducing the search space? And how is it reduced?
So the reduced search space program is in a way beyond the scope of my work.
Right, okay.
It is an established program.
But you are just following.
Yep, that I am adapting to use in a different environment.
Yeah, because I just wanted to ask. There was, I think, recently some work, right? Because Google or something that we're using machine learning to reduce some search space. So I don't have any more questions. Anybody else? Well, definitely Jupyter Notebook sounds cool to me. I'm glad that it's been similar to you. Yeah.
Of course. So the question was about our next steps and what exactly formal acceptance means and where we are right now and where we're going. So currently the program is in the final steps of development. And while the program is available to developers on the Kbase narrative system, it is not available to the general public. So our next steps will be finalizing the program and submitting it to the administrators of the Kbase narrative system for their formal review process. Once that process is over, then the tool will be public to any type of Kbase user, including biologists and bioinformaticians.
Thank you.
Thank you.
So any more questions? Okay, well, okay, let's move on to the second presentation, which will be by Lindsay Pitt on partial specifications for program research.
was experiencing. Right? So many things with everything that was my new. So to begin, I'd like to point out the program that I have is on the side, which is the extended increment is going to the side of the lateral and what we may notice is that I have a connected factor that is above the status, and instead now it says instantly. There may be other types of problems with programs other than the certain areas, which include lack of speed, which could assist with the algorithm, or there may be a type of speed. So this is a problem similarly to if you didn't know that that has an interaction at your top, then it could take you a while to figure out what it is. If you're not developers, I typically look for quick wonders like the program, so people can always be easy to be able to find it. But there is an area for search called automated programs. It's something that you can use by clicking on the program and clicking to replace. And one area that's still makes this so PD is the flexibility to connect people, and what PD does is it takes it through the facility program that I have in the last time. The main notice is that there's a lot of experience and a lot of code that ends up getting repeated, things that need to or people trying to communicate on the efficiency that's it is the case of this, we're going to be efficiency. So these notes like are removing the system is efficient at removing it. So the replacement could be something like getting rid of the A to C, replacing it with C. So you may notice, so with our original bug, its original code was replaced with different features. The code, which you can see, we can actually do is getting features. That happens to me. So with the code, you can then he doesn't know what the specific like. This is a person in practice that would be something like if the person classifies the challenges that are involved. So we'll run into the depending on the number of tests, it would give it a key. There's a problem is that it's whether we say our words in quality. So there's you want to watch there are specific issues with it, such as overfitting, which is where this is specifically a state, of the bug, because the system is able to find that like there's still lots of new bugs in state in the code. So like I mentioned earlier, if the intent is to say that would be a really an example of the way to do it. But we can see the different kind of many disabilities longer to be able to use. Many functional experiences, but sometimes there is a value here that people just isn't able to find. Then we still have to set same bugs and developers still have to be able to figure out these. There is difference between how we can get them to really be. One of these is recipe selections. Alternative systems values that I used earlier, where instead of picking a resource, that we just pick many areas and consider different times, so we get results. Then there's the several reduction, which is looking at eliminating the specification stages, as well as adding a lot of food that is not used to the separation reduction is getting rid of the one that's getting high. Developer looking at execution of the system. An automated one is the one that's done by an automated one is the progress data system. And so this basically means that if you have a system, encourages taking time to fix education support. So our idea is that we can make learning safe. So over on the side, I have an example of so this could be like a community student reliable system for the ceiling or both of the community. Get your skill in the country, has having to that passes all the the discussion idea. But we couldn't remember the pictures and the things. So over here, bottom so the original is just that original code that I showed you where it has a computation and a computer. So we're just going back to the patient and now we have content. This is where we have that I was up at the people that I have in this chapter. I found the things that all the questions are repeated, so what's really so yeah, we just get maybe also get on it. I asked the things that the questions for you, yeah, I asked me like then we have you see a description of the case of every job like a company. But when you look at the side of the table, there we have the experience of people plus the history. The eight of those is they often have a it is happening just by the similarly developed in 16 to 20 and some of these in the developed in Seattle, the question is what is it out of his mind goes into in Seattle where similarly for 16 like the years and the particular care is for this doing that. I believe that if you have self-writing culture, not but your kind of all-time if you look at that too, interview, you want to have a social context to overcome them. What we're seeing is that this starting to get a lot. So this is into the three. There's two. So use our method where we know the substances, we generate a lot of space extensions, so we'll automatically we would also take some of the this includes other systems other than triangle. These are all that we've done with these systems. There are a lot of other systems, so and also, we would like to run the always done is run it as a cookie like we mentioned earlier, but there are a lot of different tools that we have in education. Education in the future, also education presently there was a transition. Right.
Thank you. Thank you. Are there any questions?
So, have a happening is it depends on that was so even though it's
Any more questions?
so generally use that's why you think that there's kind of position in the solid water or something. When you're looking at just removing them, so only removing you just focus a little bit on removing them. So just remove it. So really yeah, if you
Any more questions? Well, let me just put a general question. So this is called a genetic improvement. So just can you elaborate on the word genetic?
growing over time and like building and improving like one that solving
I guess it's genetic. Does it take long randomness? Okay. Thank you. Any more questions? Okay, well, thank you. And with our last presentation on a minimum violation planning by Rana Srivastav.
Good morning. My name is Ganesh Srivastava, and I'm at the Department of Computer Science. And I've been working along with my mentor, Dr. Wong Kiran, also at the department. I'll be talking about minimum violation planning, which is an algorithm that helps autonomous systems decide um, how to plan a trajectory based on given specifications that may conflict with. So, like I said, minimum violation planning is an algorithm that helps autonomous systems plan out a trajectory or a path given certain consistent safety requirements, rules, or expectations. And so in such a situation, an autonomous system will have to decide which rules to obey and which rules to violate. And this is done using a hierarchy of specifications or a hierarchy of rule priority. And so to understand the algorithm well, we should first understand cost. Um, so the cost is the number of rule instructions for a particular rule and the amount of time that each of uh, the amount of time that each rule is violated for. And so this means that every rule has a specific cost associated with it. And then the total cost is a list where each element is the cost associated with a certain priority. So if we have four priorities in the hierarchy of priorities, we will have four cost values in the list. And the goal of the algorithm is cost minimization. So we want to minimize the number of rule instructions. So the least number of instructions possible for the least amount. And so over the course of this presentation, I'll be talking about this particular model. So consider a two-lane road, such that both the lanes are going in opposite directions, and you are the blue car on the far left of the picture. You want to continue forward, but the issue is that there's a red obstacle in the way, and there's two rules that conflict with each other. One is that human safety is important, and so you do not want to squeeze between the red obstacle and the lane divider. And the other is that the law states that it's not legal to cross over a solid double line. And so this creates a conflict where both rules cannot be satisfied at the same time. And so the algorithm will have to make a decision to create the most optimal path on which rules to obey and which rules to so the priorities in the current model are one, that the obstacle is not in collision, and two, that the vehicle is on the road. And these in general thought that human safety is the most important priority. The other is that the vehicle is not in lane and the vehicle is not in the clearance zone. And you can see that there are numbers next to them which show what level these priorities are at. So the most important rule is obstacle is not in collision. The second most important rule is vehicle is on the road. And then the vehicle is in lane and vehicle is not in clearance zone are at the same priority, but they are staggered inside the priority. So QLIP. QLIP is the Python implementation for minimum violation planning. It is the computer program that carries out the path optimization. So the objective for QLIP is to take in an initial state and a final state and give us a path that goes from the initial state to the final state with the least amount of rule instructions. And a reminder, the total cost is the amount of rule violations for each priority level. And so QLIP helps us to calculate the trajectory and other trivial things such as graphing the cost function or determining or showing graphically what the trajectory looks like as you see. And so QLIP does this by, first of all, taking the continuous space, because the real world is in continuous space. So it takes continuous space and generates simple random states that are distributed evenly. And this helps us to discretize the space, to go from continuous space to certain chunks that help and which help us to process the entire region. And then each requirement that we wish to fulfill is given a priority, where the cost for violating a more important rule or expectation is higher than violating one which is at a lower. So the algorithm then generates a durational cookie structure, which can be thought of as a graph. And this durational cookie structure takes into account the set of all states. So that is the discretization I was talking about, the initial state, which is where the autonomous system is going to start. The transition from one state to another is how the information about each state and a label assigning function, which is what priorities are fulfilled at a certain randomized state, and the time value, which helps us to calculate. And so, given all of this information, the algorithm works to find the most optimal path, minimizing the rule violation. And so the algorithm works in 4 distinct steps. First, it initializes all the necessary variables, and we have a list of elements that track our trajectory. And so we add the initial state of the system into the trajectory, and then we randomly sample new new states. And for every state that is sampled, we look for all the nodes or states that are closest. And so for each state, new state that we sample, we check if there is a valid trajectory from the node that we sampled to previous node. And if such a thing exists, then we add it to the trajectory. And we then check if the newly added node was a part of or was the goal state. If it is the goal state, the algorithm does not terminate. The algorithm goes back to optimize the entire trajectory, and if not, it continues. So I'm going to go through a very quick example. So the goal in this example is to go from the initial state in blue to the final state in red. And so that is priority number 1. The second priority is to stay between the 2 lanes, which are denoted by the solid white lines. And try to stay in the left lane or the top lane. And so this is the discretization of the states that I was talking about. And these are the states that are available to the system. And so we sample a new node, and then the algorithm looks for a node that is closest to it, and it identifies this based on distance. And once that happens, we identify the node that is closest and has the least cost. And once that happens, we add it to the trajectory. And since no rules are violated, there is no cost associated with this particular transition from the initial state to the first node. And then this process is repeated. So we sample a new node, look for the node closest to it, and ones that have the least cost. And then we go to this, and there is a cost associated with this transition because we're changing lane. And so the cost in this case is time that is spent in the other lane. The process is repeated. We find the nearest node, and in this case, the cost is the time spent in the other lane and the time spent outside the road boundary. And so this process is repeated again until we reach the final stage where the final state is a newly sampled node, but we don't know it. And then we look for the closest one and we add it to the trajectory, and then we check if this is the final state. And if it is, then the algorithm goes on. So this is the output that the algorithm generates. So this is the sample space after 10. And so on these pictures, you see dark blue dots. The dark blue dots are the space discretization that I was talking about, or randomly distributed states. The cyan or the light blue curves that you see are the transitions from any one state to another. The black curve is a trajectory that the darkest blue bar on the far left will follow, and the red bar is still the opposite. And so we see that for this, it generates a path that overtakes and goes into the other thing, which implies that there's going to be a cost. And so the cost in this case was 28.3 and 63.9. And this is the sample space after 10 iterations. And so the time to go from one iteration to the next, or from the 9th iteration to the 10th, was 1.5 seconds. Similarly, in the second example, or the picture on the right, you see that there are 2 obstacles that the car has to navigate around. And it goes through, and on the right-hand side of the picture, you see that there is a large gap where it goes through and crosses the lane, but it had no need. And so this goes to my point that the more number of discretizations or the more or the richer the sample space, the better it is. And so we repeat this process for more iterations. You notice that this path is quicker and more optimal than the one that was implemented. But you also notice the cost increase. So the cost in the first slide was 28.3 and 63.9 for the picture on the left. And over here it's 11.6 and 37.2. Similarly, for the other one, it was 43.4 and 61.3. And after 20 iterations, it's 40 and 60. So this says that running more iterations gives the algorithm more opportunity to connect to more states, and so the path is more optimal as time progresses. So some practical considerations. In the real world, there's only so much available computational time, and a real system will have to deal with everything very fast. And minimum violation planning achieves this because the predecessor algorithm had a worst case time complexity of k squared n log n. But minimum violation planning has a time complexity of n log n. So it is faster by a factor of k squared, which is significantly faster when the greater the number of sample points you have, the better your algorithm functions. And the other is the limitations of the cost function. But how well you define your priorities and how well you define the cost function will also determine how well the algorithm gives you the expected or intended result. And so over the course of the last few weeks, I've been working on studying the interactions between different agents in minimum violation planning, and I will continue to do so in the next few weeks. But I will study the interactions between dynamic agents in minimum violation planning. So two cars where both of them independently implement minimum violation planning. And so this will help us learn how the cars behave. Do they behave in a greedy way where they want to take up the entire space themselves, or do they work in a more cooperative? And then my next step after that over the summer is to implement TULIP on the DuckyTime, which is an autonomous system modeling suite. And so this will help us to test it, and it works as a proof of concept and as an excellent output of it. And a far-reach goal is to generalize the cost function. The cost function right now is based on time, and so over time, we would like to generalize it so it can involve. So, any questions?
Are there any questions?
Yes. That is a great question. So the question was if it's possible to run the simulations beforehand, and so that will reduce the amount of time it takes to perform calculations. Did I get that right? I'm not exactly sure, but yes, that could be possible, and that will help us to reduce the time complexity. So not everything has to be calculated in real time, and so that will improve the functionality. But I'm not sure how that will take place since I haven't worked on that.
Can you both go back a couple of slides?
Yes.
But more. Yeah, come here. So you are generating this random state.
Yes.
How are you doing?
Oh, so it is a simple random function that takes a random value for X coordinate and Y coordinate, and then takes it, and it's given certain limitations. So it will only do so between the space that we give it. So we give it two constraints, and it generates random points.
Right. So anyway, just my comment is that the way you generate these random points, it may be from a specific distribution, it may be better than just a completely limited. So you may be trying to adaptively generate the random points that if you generate them in a smarter way, it may impact. That's nice. Okay, just a simple question here. So I guess you are violating the basic rules when you are crossing this here, right?
Yes, because it has to, like,
I know. All I'm saying is, in practice, I guess you would have a camera or something, whether they don't come in.
yes,
Yes. Yeah. Okay. Anyway, so yeah, my comment or suggestion is just maybe the way you generate this random points.
okay.
That's a common trick, right? Sampling, right? So any more questions? If not, then we are ready to conclude the discussion. Okay, thank you, speaker. Pleasure.